So I am very keen to find out who is coming along to the workshops that I run. So we're going to have a little bit of interactivity to kick things off. Please put your hand up if you are a data scientist. I want to know the roles of, okay, lots of data scientists, unsurprisingly. Machine learning engineer. Who describes themselves as a machine learning engineer? Okay, who is a software engineer? Okay, welcome software engineers. Is anybody a different role, like head of data, business owner, data analyst, anything else in the room? Okay, yeah, so engineer, data engineer. Wonderful. So we all, a lot of us, probably build algorithms. Who's written an algorithm before? Okay, and that's then actually been made to go into production. It's therefore impacting people's lives. That's what this is all about, because algorithmic harm is real. Is there anybody here from the Netherlands? Put your hands up. Okay, so two very keen people. So I think this brought the Dutch government down. There was a scandal a few years ago where there was a welfare benefits fraud detection algorithm that went sort of wrong, and it resulted in tens of thousands of families being accused of benefits fraud, over 1,000 children being taken out of their homes. Okay, so this is what this is all about. Algorithms are amazing when they work and can cause massive harm when they don't. So first things first, if you have questions, put them in the Slack. I will answer all of them at some point today. I will also be hanging around after the end of this workshop to answer any questions you have in person. There is a repo, so get to the repo. If you miss it, the link is also in Slack. Or you can GitHub my name, John Sandall, and you'll find it there. So algorithmic bias, it is a thing, it's real. I uploaded my CV with my name redacted to ChatGPT, and I said, draw me. And this is what it thinks I look like, which when I'm presenting at a more corporate conference, it actually got the suit perfectly correct. But otherwise, this is, I guess, ChatGPT's definition, internal definition of your average Hollywood casting AI CEO. And maybe that's not a good thing if we're using LLMs to be making decisions about people, if it just assumes that the right person for the job is the Hollywood casting version of that person. I actually with her permission, my partner's CV through this as well, name redacted. Create an image of this person. Now, she is a tax technology person, tax background. This is what apparently it thinks she looks like, weirdly similar to the AI version of myself. So again, Hollywood casting version of a tax technology lead. And maybe this is not good if we want to use LLMs to make decisions about people's lives, whether it's going to be for hiring or whether it's going to be for other things like welfare benefits assessment and fraud detection, if it's making assumptions about what those people are and who they look like. So a little bit about myself. As mentioned, I run a consultancy called Coefficient. I'm also heavily invested in the world of PyData London as a co-organizer. So thank you for coming along to what is my first ever workshop at the PyData London conference. And over the last year, my company was engaged by the Department of Science, Innovation and Technology in the UK, along with the Equalities and Human Rights Commission and the Information Commissioner's Office, to look into the world of AI fairness, to develop new and novel methodologies for evaluating fairness, for mitigating fairness, but also with a very specific lens of looking at fairness in hiring. So we're going to have a very, very specific hiring slant in this section, because this is the expertise that we've developed is some of these techniques. And we're sharing some of this with you today. So again, get the repo while I'm talking through this next section. Install the requirements, get everything up and running. There's a Jupyter lab, there's some notebooks. So get that going, because this is going to be a fairly pacey session. So whilst you're doing that, a little bit of AI fairness, a brief history. So the first thing that's worth knowing in the world of AI and recruitment is that 72% of CVs are never seen by human eyes. And that is a decade-old stat, so it's probably way higher than that now. And I don't know, who's done hiring for their company before? Who's actually had to do this? Okay, so a bunch of you. You have applicant tracking systems. These days, the applicant tracking systems may have an AI recruiter that just lands CVs into your inbox from God knows where. How is it selecting those? Is that fair? Who's looking to assure if that's fair? Huge questions. You may even have a CV scoring tool built into your system. And there are lots of different places that we looked at within the algorithmic hiring pipeline, whether it's sourcing, talent discovery, anonymization, which apparently fixes everything according to some of these vendors. It doesn't. You can anonymize someone, and I still know a lot about who they are. If they were studying I don't know, if they were playing in the Oxford men's rowing team, I think we can make a rough guess as to what their gender may have been. So anonymization doesn't solve this. CV passing, CV screening, but also candidate ranking, shortlisting. There's a few other sort of slightly curious applications of AI these days in the world of recruitment, such as being able to, I don't know, scan your micro expressions whilst you're on a video interview. There are tools that do that. Whether they work or not and whether they're ethically okay or not are different questions. So a little bit of history of, in this world, employment and bias, because it does connect all the way through to 2025 and algorithms, is the first ever time someone thought, hey, maybe we shouldn't have bias when it comes to, for example, hiring people. So one of the seminal things in employment regulation anywhere in the world was in the 1950s, Duke's Power, downriver steam, basically a power station. And they restricted their black employees to their labor department, the one with the lowest paying jobs. And a few years later, they mandated, they kind of got tougher on this, you must have a high school diploma for employment in those better paying departments, basically intentionally limiting opportunities for the black employees. Then in 1965, huge regulation in the US came in through, the Civil Rights Act. And on that same day, to comply to just about the letter of the law, they added an aptitude and IQ test, saying, well, we're not mandating a diploma which these black people may not be able to get, we're going to give them an aptitude and IQ test, but those tests disproportionately disadvantage the black employees. And what ended up happening, it took a while, another 6 years, but it went all the way up to the Supreme Court. So they ruled in favor and established this thing called the disparate impact doctrine, which basically is that even if you're not intentionally trying to discriminate, because that's very hard to prove, if the outcome of what you do when you're selecting for people in your promotion process or your hiring process is that it does actually discriminate disproportionately, then the burden is on employers to justify those practices. And that still stands today in the US, and very much applies to AI hiring systems, many of which may be falling foul of this particular disparate impact doctrine. So landmark ruling. What about does anybody know where the world's first AI hiring scandal, real AI hiring scandal happened? Anybody? This beautiful city, London. 1979, St. George's Hospital. Good on them. They tried to take all of their historical graduate admissions data for the medical doctorate scheme, and they loaded that into a little NLP classifier, threw it into I don't know what, random forest, maybe. 1979, maybe something simpler, but whatever they did, they built a replication of their human decision-making using machine learning techniques. And some of their internal team blew the whistle. Again, it took 7 years to do it, but they did an internal investigation. They realized that this system was systematically discriminating against applicants with non-European names and women, regardless of qualifications. But it was replicating the staff decisions with 95% accuracy. So as far as you're concerned in terms of your ML evaluation metrics on your supervised labeled data set, that looks great, 95% accuracy. But it's really, really biased and harmful if you care about these things. So the Commission for Racial Equality looked into this. They said, yes, there are definitely at least 60 people who should have got the job who didn't. And no fines were levied, not much happened, but it did sharpen best practices for academic institutions in the UK. If you're really interested in this world, really recommend the AI Incident Database. It's full of more horror stories like some of the ones that I've just mentioned. Final little horror story, more recent, Amazon testing their AI hiring algorithm. So this blew up in the news in about 2018. I think maybe the approach they took to this was not best practice. They wanted it to be an engine where you just give it 100 resumes and it spits out the top 5 and you just hire them without any human oversight. And it turned out that women were penalized. Having the word woman in your CV or anything that transpired that it could figure out that you were a woman would mean that you were penalized and your chances of getting the job at Amazon were much lower. And again, anonymization doesn't help here. It can figure out, an LLM for sure, but even machine learning algorithms can figure out things about your protected characteristics and your demographics based on what you've done, the clubs and societies that you were at university, the things that you've done in the meantime. Even how you write can be linked to demographics sometimes. So what is happening in 2024? You've got amazing AI tools. Some of them are useful, some of them are potentially discriminative, and the thing is we don't really know because there is no regulation or legislation that is forcing these organizations to assure their AI systems yet. There is regulation coming in the EU's AI Act next year. It'll start to bite, 35 million euros maximum fine for someone who is in breach of creating an algorithm that causes harm at a societal level. So this is going to get some teeth in the US. They're going in, I guess, a different way. But there's loads of these tools out there. If you are building an AI-powered platform, then again, we've got the hiring focus, but these techniques you can take away and take home and apply to what you're doing at your work. And some of these, like I say, are doing video interviews, they're scanning your facial expressions, they're doing psychometric testing, all powered by AI, but we don't know if it's fair. I don't know if they're looking into this at this level, because why would they? They're not incentivized to. They're incentivized to get their next funding round. So that's the background. Now time for a lab. Has anybody got any difficulties getting the repo or setting things up? There's a few different ways. You can pip install, you can poetry install, you can UV install, or go your own way. But any issues, just raise your hand. OK, what I'm going to ask is, are you asking where the repo is? If you look in the Slack channel, there is a link in the Slack channel. If you notice that someone nearby you looks a bit confused, looks like they're struggling, they're trying to get Jupyter running, just keep an eye and help out your fellows in the room, and just be really handy and help me out as well. So into our lab, testing fairness. So the code is here again. What we're going to do is I'm going to walk you through. Now this bit is sort of less the focus, but still a critical part of doing any fairness testing is having a good testing data set. So I'm going to walk you through how we go and create a testing synthetic data set. Now, obviously, if we're doing this for real, like the work we did for DCIT, we were using as much real CV data as possible, working very close with the ICO to ensure we weren't breaking GDPR rules and guidance. But for a workshop where I'm sharing data, I obviously can't do that. So again, we've got a synthetic data set created just for this workshop. So I'll walk you through it, but the high level is we're going to create some CVs. Some are going to be high quality, some are going to be very low quality. Then we're going to create some synthetic characteristics. So we're going to have women and men just for today. But you could go deeper, you could add ethnicity, other protected characteristics in the UK, things like religion and disabilities and more. Then what we're going to do is we're going to start injecting clues as to what someone's background is. So we're going to actually use a lot of OpenAI for this. That's another heads up. If you don't have an OpenAI key and you don't want to use OpenAI, then just feel free to sit back, watch. You'll see me run through lots of the demos. When we get into the part 2 lab, you can just use the data set that's already in the repo, which is much bigger. So you don't need OpenAI, but you might want to drop your OpenAI key into your environment if you want to follow along and generate your own synthetic CVs. I also highly recommend in the code playing around with it. Make it your own. I've made software engineering CVs, but you could make machine learning engineer CVs. You could make, I don't know, head of data analytics CVs. You could make puppy trainer CVs. I don't care. Have fun with it. Make it your own. And you also don't have to stick with the demographics that I've come up with. So if you wanted to do it on something other than gender, then play around with it, make it your own. But we're going to keep it simple. So male and female, we're going to ask GPT for clues. We'll see if those clues are actually reasonable or not. And then we're going to simulate a recruitment process where a recruiter is incredibly biased. If they were caught out by the EHRC, they would be fined for selecting men at a 99% rate versus women at 30% rate for a similar quality of CV. But we're trying to create a biased data set to replicate typical human decision making because not quite this extreme, but this is what human recruitment teams do. They are biased. There's lots of research that proves it, and we'll cover some of that later. So let's see some of that in the code. If this is too small for anyone, I can make it a little bit bigger. Just wave at me. OK, so just for this demo, I'm going to create just a data set of 12 CVs. The data set that you actually have in the repo, we have a much larger one for part 2 of this workshop, which is 400 CVs. But that takes an absolute age to build and run because it's all coming out of OpenAI. So feel free to run with 12. If you really want to go for it with your puppy trainer CV selection program, then you can set this number to 400 or 200, which should be enough to actually see the biases coming through when we train an algorithm on it later. So we're going to load in the OpenAI key. I've got this in my environment. You can either just supply it directly, copy paste it, or you can put it in your environment as well, and it should come up. So we've got a little algorithm here. This is going to generate a CV. It's just a big old prompt. We give it a high or a low quality. And I've defining high quality as like 8 to 15 years, top tier software engineer, or 1 to 3 years as, again, I don't mean low quality, I mean just someone with less experience. But it should differentiate the CVs quite meaningfully into a higher and a lower quality of CV or more or less experience. And we've got a fun little system prompt, and you're a professional CV writer, et cetera, et cetera, et cetera. And then we're going to use GPT-4o Mini. Feel free to change that to your own preference. And we're going to extract the response. So let's see what it looks like. Generate a CV. high and low. Should take 5-10 seconds tops. And if you want to format the markdown that comes out, there's a few markdown converters. I'm going to use the DigitalOcean one just because it's fun to look at. So I can take this. We can see what this looks like. It's in markdown. It doesn't really need to be formatted for the purposes of training a model, but it's fun. So we'll see what this looks like. OK, so here's our high-quality CV for a software engineer, a dynamic and resourceful software engineer with over 10 years of experience. They know Python and Java and JavaScript and C# and TypeScript and all these things that the AI has decided a experienced software engineer should look like. And if we compare that, do we have a reasonably lesser qualified software engineer? Hopefully we do. So again, we can just compare that. And you'll see that this person is, they're currently a junior software engineer with 2 years of experience. So we've got a system that can generate a very differentiated set of text data, which maps onto higher or lower quality of hires. OK, so what we're going to do now is going to create an equal number of those and stick it all in a big data frame. I'm going to have this data set be completely balanced. So there's going to be 6 men and 6 women. And then those are going to be 50-50. So 3 high-quality male software engineers, 3 high-quality female software engineers, and then the same with the lower quality. You'll see that come through here. Then what we're going to do is start generating clues for the models to pick up on. Now, one of the things that you'll find out is the clues that we're injecting when we were doing this for DSIT, we were very subtle. It would be literally, they were part of a university club, or they might help out at their church at the weekend of their mosque. These would be religion-based clues that we could just inject, and at scale, an LLM, because we were doing fairness testing on LLMs for DSIT, an LLM would be able to pick up on that, and it might start making its own biased decisions about whether someone who attends their mosque every Sunday is appropriate for a certain kind of role. Now again, according to the UK law, it should have absolutely no bearing and you cannot discriminate based on that, but an LLM, it turns out, definitely does. So how are we generating our clues, just while the last bit's running, is, again, we're just going back to OpenAI, and we're saying, create me a paragraph of text which is highly indicative of, in this case, sort of a male software engineer, and versus female. And again, what we're going to find is that, as I mentioned, LLMs are biased, and the text it generates, I would say, is pretty questionable. So this has started running. We've got the CVs, they're in a data frame. You've got the mapping of whether they're high and what the sex is of the person. It's completely equal numbers, 3 of each in this data set. And there's going to be 400 in the next data set, so 100 of each. So let's try these clues. So we're going to have a clue for a man, a results-driven software engineer with extensive experience and proficient. And it's got a certain style of language that it might use. For some reason, the LMs decided the female software engineer, rightly or wrongly, is much more passionate and active participant in hackathons and supporting gender equity. And, oh, this is Hollywood casting versions of men and women software engineers, it turns out. Just like LLMs have this kind of problem. They just assume this strange average version of what you're talking about. And if they're being used to make decisions about people's jobs and future careers, then that's maybe an issue, because it shouldn't be biasing on this basis. So we're going to generate a bunch of these now, and we're going to start adding them to our CV text. Now, one of the things that we have to do, just for this workshop, is these clues are so subtle that the kind of idiot classifier we'll be using in the next section, which is just a NLP text classifier. It's nothing too fancy. It's a bit of scikit-learn. It's not smart enough to actually pick up on things like active in STEM-based diversity initiatives. So we actually just inject the word woman in there just to make it really obvious. These are women. Don't you dare discriminate on that, but if you want to, you can. So just for the purpose of this workshop. So now we're going to simulate the bias recruitment round. I'm just going to bring up these slides so you can see what it's actually doing here. When it sees a man at the higher quality, they're going to be selected through for an interview 99% of the time. When it sees a woman at high quality, it's 1 in 3 times. When it sees a man at the lower quality level, it selects them through at 40%, and if it's a woman, they never get through. So this is actually now, at this point, we're injecting bias into the data set. We're going to replicate St. George's Hospital back in 1979 with their however many years of making biased decisions. The only way the algorithm was biased is because they trained it on biased data. So this is what we're doing here, is going to create that biased data. And then we're going to start adding names as well to these that are aligned with this. Again, this is a best practice in discrimination research. Is the best clue that you can give to these sort of algorithms or people is actually a gender or ethnicity aligned name. And I'll give you a few examples of how that's been done in academia previously. So we've got our bias recruiter function. We're going to decide callback is just whether you get called back for an interview having submitted your CV. And that's sort of gone through that probabilistic function. And what we find is that, yes, the men are being selected through, the women selected through at a much lower rate. And if they're a low-quality women, it's 0%. You never have a chance. So now we're doing the extra clues. This is going to be adding names, and those names are going to be gender and ethnicity aligned. So again, this is, I would say, a fruity area of trying to do research right. We are led by academic best practices in the non-AI world. So what we're doing here by injecting names into CVs to see if people are called back at different selection rates, this is a totally standard thing in the world of discrimination research. The government has done it, DWP has done this, academics have done this. This is sort of how things are done and proven that humans are kind of discriminative. So what we've done here is we've loaded in a data set from one of these published academic studies of some of the top men's names aligned to ethnicities. These are actually more US aligned names. They're coming out of some US census data. And same for women. So you can see the men are Adam and Aidan. You've got black men, Akeem and Alfonso, Adrian, Alan. You can see sort of there is these differences here between the ethnicity by gender. And again, at scale, LLMs are going to pick up on that. So we're going to add some racial information. We're going to then add the names to the CVs. And so what you see here is every CV. We're building up this amazing data set where the CVs now have an assigned race, name, selection, callback, and gender and quality. So let's have a look at one of these. This is now a finalized CV. It's a woman. It's got the word woman just at the bottom. And we can now see how it looks like. So let's take a look at Kelsey. AI-generated Kelsey. So Kelsey is a senior software engineer, results-driven, innovative, the rest of it. This is all completely generic to a high-quality software engineer. You've then got the paragraph at the bottom, which is trying to inject additional clues into her gender. Although to an LLM, the name is going to be enough, but we add this as well. And then we've also just got the word woman, just so our kind of simple decision tree classifier can actually pick up on that at least. OK. So where are we at? We've added the names. We've got our finalized data set. Now, if you're following along, you're generating these for yourself. You've got your puppy trainer data set chunking through. Then feel free to use that. You're also welcome to, in the next stage, load in my version. So if you hit export, what you'll also see is there is a version in the repo, in the datasets folder, datasets output folder, which has actually got 400 CVs pre-generated aligned with the code. So you can also just pick up on that in the next section if you haven't been able to quite follow along. So a little bit about fairness research methods. Like I mentioned, in the world of non-AI research, so when we're looking for analogs of how to do this for AI algorithms, one very good place to look at is in your industry, how are things done in the pre-AI world? Because again, it's really hard to know how to do this. How do you do this ethically and morally and correct? It's really, really tricky. I kind of sweat the details and fear like we're doing things wrong. So we looked at what's done before. We looked at the literature. So the landmark study in the field, the one that's cited more than any other study, is this one here. It's a field experiment on labor market discrimination. Are Emily and Greg more employable than Lakeisha and Jamal? And so what they were doing is identical CVs, but they were just switching out the names for ethnicity-aligned names. And they were fictitious names, and then they were just sending them to help wanted ads in Boston and Chicago. And what they found is resumes with white-sounding names had 50% more callbacks. This is humans. This is not even AI yet, but it's humans doing this, than those with African-American sounding names. White people with higher quality resumes got 30% more callbacks than those the African-Americans with a high quality CV. It was discriminated on the neighborhood that you were from. Even the federal contractors who are legally mandated to be an equal opportunities employer were equally discriminative as the other employers. So discrimination consistent across every single industry and occupation that they looked at. What about in the UK? So as I mentioned, the Department of Work and Pensions funded a similar study, testing for racial discrimination in British cities. Very similar approach that they took. They had identical CVs, and then they were just injecting clues into someone's demographic background into these. And then they did this across 9 different job roles in the UK. Fired them off to real organizations, saw who got called back for an interview. There was a very careful, it was a really fun study to read. This is all on gov.uk, but a very careful way to select names that are completely aligned in people's minds. They did multiple rounds of YouGov surveys to figure this out, and then they were using these names as the clues. And that was the only thing that was different between them. And again, similar studies. So the white applicants receiving significantly more positive responses than ethnic minorities, literally almost double, including a 29% net discrimination in favor of white applicants. I'm going to point out that stat there. How do we test for fairness? This is one of the ways. We're going to go deep into fairness metrics shortly. But this is one of the ways is you look at the outcomes for equivalently aligned people, and you see if those outcomes, there is a disparate net discrimination between them. Public sector organizations less, but still discriminatory. So this is a problem because if you are trying to build an AI hiring tool, what data are you using? Because it looks like every data set you could look at is going to be somewhat discriminatory. At least any of these organizations, it looks like humans have a hard time of removing our own internal biases. So how do we even do this? Back to the lab. So if you have been following along, the last bit of this was just to export the data. You can save it. It saves out as resumes.feather, a little feather file or CSV, but I like feather because it won't mess up my data types. But at this point, you can load up the model notebook, this one here. And what we're going to do is we're going to now run through the motions of being a not well-informed data science team at one of these sort of AI hiring companies. And we're going to train a model on exactly the data set we've just made. And we'll see if it encodes those biases into the model. And then we're going to learn about how to remove them. So in a real application, you definitely don't want to do this. Don't do this at home or work. This is purely for workshop purposes, because we need to start with a very, very biased model so I can show you how some of the debiasing techniques work. OK. So we'll bring on our imports. And we're going to test a few scikit-learn models and a light GBM model. What I'm going to do is just a little bit of text pre-processing here. I'm going to remove some white space that I don't care about. I'm going to just clean up the CVs, remove lots of punctuation. That's what this is doing. Now, if you want to use your version, change this bit of code here, where it says resumes 400, and just remove it to resumes, and that will use your version if you've generated one. If it's only 12 CVs long, it may not work very well. So maybe if you want to follow on, use this one. If you've been busily churning away, getting OpenAI to generate your puppy training CV data set, then actually you can use your version instead. But you probably do want at least 100 or so for it to pick up on the biases. So we're going to read it in. Let's see what our data set looks like. Again, it's just the same old DF that we saw just a few seconds ago. So we've got the CV, we've got all of those clues, and we're going to just double check what is the selection rates. This is what you saw momentarily ago, that the men are being selected for much more often than women in a completely discriminatory fashion, because there's nothing that differentiates the men and the women in this data set other than the clues that you are a man or a woman. So let's build our terrible model. The model's getting just the text. That's all it's getting. It's not getting the gender. It's just getting the text and the callback. We're going to have a little count vectorizer. There's nothing particularly fancy in here. Remove some English stop words. And now we've got a nice feature matrix with all of those stop words. So you can see the sort of things that are going into it. And it's definitely selected for the word woman, because that comes up a lot. But also things like years experience, AWS, proficiency, those sort of words will come through too. So the baseline callback rate across the entire data set is 41%. If you were doing this on your own company's hiring data, A, double check that you're allowed to do that according to GDPR and sub-data processing rules. But B, this might be where you start. You may not have a good data set of their demographic backgrounds as they came into the process. All you're going to see is this. Here's the data set. The baseline callback rate was 41%. Then maybe you might do this. Let's try a decision tree. And surprise, surprise, this is why we did it. The word woman is the most discriminative feature for quality or selection or callback. I'll say callback, not quality, because they are no quality difference in terms of their CVs to the men. So then if you are a woman, your odds of selection goes from, this is 165 out of 400, so about 41%, all the way down to 27 out of 200. So 40% down to 27% just by having the misfortune, according to this data set, of being a woman. Otherwise, if you're a man, it's going to start asking you about your technical qualifications. If you know Docker, apparently that's good. And all of the Docker people actually get called back, according to this system. But other words, tech, teams, they might be discriminative as well. Agile methodologies improve. Again, these have come back as usefully discriminative keywords, according to this text classifier. So again, we can see what is the callback rate on average. It's about 70% for men. It's about 15% for women. And we can also start splitting this out by some of these keywords. So for example, if you mention AWS in your CV in this data set, then if you are a man, mentioning AWS is great. You get the job. And if you're a woman, then still less than 50-50 whether you get the job. So very, very big differences. And this is why that's come back as a discriminative and useful predictive feature, because it does completely differentiate between who gets the job and who doesn't get the job. So not just your gender, which again is hidden to the AI algorithm here, but also the keywords, obviously, are markers of experience. So now we're going to find a really good bias model. Decision trees, it's not going to be the best kind of model. Let's train this model for accuracy, is what we're going to use here. So the dummy classifier would be about 59% accuracy. We can boost that to 80% with a random forest classifier. We can get to a similar level with a decision tree. We can tune the decision tree. We can get it a little bit higher, 81%. Or we can have the Blue Peter. Here's one I made earlier, LGBM classifier, the light GBM classifier, which gets me to slightly higher, about 82%. So I'm going to stick with that as my model. I'm sure you could make a better model if you want to, but the purpose is just a good enough model. It's reasonably accurate. I don't know what it's looking at, but it's reasonably accurate at spotting the kind of people that our awful recruiter was selecting for previously. And now let's actually look at what it's looking at. So the light GBM, we're going to use some permutation importance and figure out what's going on here. Okay, so again, unsurprisingly, just like the decision tree, and because we stuck it in so aggressively in as a keyword, it's making a lot of its decisions based on whether you're a woman or not, or have the word woman. Then otherwise, it's words that are generally aligned to probably appearing in those higher quality 10 years of experience versus 2 years of experience CVs. So if you're an architect, if you're developing technologies, microservices, apparently it likes, Scrum even apparently is a useful word. Again, these are high quality in terms of their feature importance. So I don't know if Scrum is going to help you get the job or helps you not get the job, but I don't know. Feel free to check out my previous PyData talk on Agile and Scrum if you want to see what I think about that. So architect is one of those critical words here, and you can see why. Again, very discriminative. If you have the word architect in and you're a man, you basically get the job. If you don't, 40%, you still get the job. If you're a woman, and you are an architect, or you have the word architect in your CV, then you've got less chance of getting the job than the man who doesn't mention it at all. So again, we've got good bias coming through in our data set. We have successfully created an awfully biased situation and an awfully biased model. So let's talk about how we measure bias. This is going to get a little bit statistical, so hold on to your seats as we jump through the wonderful world of fairness monitoring. So what is fairness? What is equality, equity? There's lots of sort of definitions. This is sort of borderline quite political, but broadly, and I try and be sort of a good statistician and say objective here, equality is all about treating everybody the same, giving them the same treatment. Equity is about giving them the access to the same opportunities and outcomes, regardless of their individual circumstances. And a lot of the time, when you're actually facing sort of equality or equity issues, potentially actually just trying to figure out why the hell is there a fence in the picture at all is maybe the bigger question, rather than how you figure out how to treat people in different ways. But what about as statistically? There are lots of different metrics we can look at. So if we're looking for a difference in outcomes of what? Is it the model is more accurate for men, or it's selecting for men more often? Is it about sort of false positive rate, false negative rate. So if you have a model that selects lots of men through for a job when they shouldn't have been, then it means that men are going to have a very high false positive rate. And if it doesn't select the women through, then actually they're going to have a high false negative rate. So if you compared the false negative rate for men versus women and the false negative rate for men versus women, the men have a very high false positive rate. They're getting the job when they shouldn't. The women have a very high false negative rate. They're not getting the job when they should. So that's one example. But there's a lot of other metrics we could look at. So what are the metrics that are currently considered? I'm going to give you an example here. This is a historical case study. Some of you, if you've sort of been following this field for a while, will know it. This is the COMPAS case study about predicting recidivism, and also quite relevant in the UK now that there's a whole big hoo-ha around who do you release from prison early, and the papers get very upset if you release someone from prison and they go on to reoffend. So that's what this is about, recidivism. And in the US, they use algorithms to decide how long someone goes to prison for based on their likelihood of reoffending, their likelihood of recidivism. So is this a good use of algorithms? I don't know. Maybe, maybe not. Certainly, historically, the algorithm, if it's biased, definitely not. So the rate of recidivism in the US is 70% within 5 years of release. So this is a challenge. How long do you incarcerate someone for if there is a 7 out of 10 chance that they will reoffend within 5 years? So the software that they use for this, ProPublica, did some amazing investigations, and it was unsurprisingly incredibly biased against black people. So what are the metrics you could look at here? Let's put our stats hats on. False positive rate, false negative rate, false discovery rate. 3 different metrics that were argued as relevant metrics in the ProPublica case. False positive rate, basically, in this case, you've got the people who were going to be good. They were not going to reoffend, and the model thinks, no, you are guilty before you've even done it. Okay, so the false positive, it's going to accuse people of reoffending when actually they wouldn't. Okay, so if you've got a higher false positive rate for black versus white, then that's going to be locking up the black people for longer, because it's going to be basically treating them as criminals before they even do anything, or rather when they wouldn't have done anything. That's why it's a false positive. False negative rate, you're basically giving people a free pass. You're saying you are going to reoffend, but our algorithm thinks that you won't. So again, if the false negative rate is lower against white people, it's letting them out earlier, and then they're reoffending. And the model's like, oh no, I thought you wouldn't do that. So again, problematic if this is racially biased. And then false discovery rate, amongst the people that the model thinks will reoffend, how many actually do not. So almost sort of an inverse of false positive rate. What is the harm in each of these cases if you get it wrong? If you get the false positive rate wrong, then someone who would have come out and stayed clean, they're going to now be locked up for longer because your model was biased against them. Bad luck for being unlucky. False negative rate, you're letting people out and they're going to go and commit crimes. False discovery rate is actually the same harm as FPR, because it's sort of a similar metric. So in the COMPAS ProPublica case study, what happens is they looked at these numbers, they looked at these metrics, you compared it, Caucasian versus African American, and you can find that the false positive rate is much higher, almost twice as high in the African Americans versus the Caucasians. And the false negative rate is almost as much higher in Caucasians than African Americans. So what they basically said is, you are looking at a black person and everything else being equal, you're saying lock them up for longer because they're going to reoffend when they won't. And then you're being completely the other way with the Caucasians where you're saying let them out. They're going to be fine. And then they go out and commit more crimes. So this is problematic. But the people who built the algorithm said, nah, false discovery rate is basically the same. So we're fine. This is the metric we optimize for. So why are you angry? So is it biased? Actually, you can't achieve fairness on all 3 of those metrics. I'm going to sort of whiz through this, but I'll share my slides if you want to sort of go through the maths later. These 3 fairness metrics are mathematically incompatible. What is false positive rate? It is a combination of false discovery rate and false negative rate. Okay, these things sort of might multiply out to go from one to the other. So if some of them are high, some of them are going to be low by mathematical just definitions. So it's not possible to have all of them be low. Just, you can't have both. So how do you even answer this? Do you go with the COMPAS algorithms creators and they say, yeah, look, FDR is equal, our system is fair? Or do you look at the other ones? But you can't look at all. This is hard. I've got some answers for you, but this is hard. Because there's more fairness metrics besides, not just looking at FPR and FDR and so on between these different groups, but you can look at demographic parity. So the outcomes, are the outcomes equal between these two different groups? And you can get intersectional here. What about black men versus Caucasian women? And what about if you start adding even more intersectionality in terms of disabled white men, disabled old white men versus young non-disabled Asian women? Again, like there are a lot of different combinations here where you can have potential disparities in terms of the outcomes. Now, if we go back to the hiring example, the outcomes we're looking for are you selected evenly? If you have identical people go through and one of them is called Jamal and one of them is called Paul, are they getting the same likelihood of being selected through, especially if you've got that sort of analysis happening at mass? Problem is, you may not want to be optimizing for equal outcomes. There are situations, I'll give you a really crude one, in the world of an airport security screening role, you need to have a woman who is there to screen women. Like that is a legal requirement. So you can't have a role where you say, oh, men and women need to have equal opportunity or outcomes for this particular role. It's a role that is legally allocated to one particular sex. So there are other situations where you don't necessarily want to optimize for equal outcomes. That can have its own unfairness. Then another way of measuring fairness is counterfactual unfairness. Now, if you are developing AI models, then you can do this. This is a really cool technique. I think it's underused historically, but you could do this because you have access to your model, and you can use the techniques I'm presenting here today around synthetic data generation to generate counterfactual examples. Okay, what happens if we take our last 6 months of hiring and we change some of those men for women? We actually simulate alternative universes, alternative timelines. That's counterfactual fairness. You can't do that if you're analyzing just a real-world data set as easily, and you can't do it if you don't have access to the model or the decision-making system. So it can be difficult to assess these, but if you do have access to using synthetic data to create counterfactual scenarios and the model, then you can see if the model is genuinely making a different decision based on whether your name is Jamal or Paul. And then finally, there's equality of odds. This is used quite heavily in this discipline. It's sort of a bit of a complicated sort of definition, but it looks at your false positives and your true positive rates, looks at those rates for people who have a true positive outcome. So in the recidivism case, you look at the people who did reoffend, and then just in that subset of your population, you look at their false positive rate and the false negative rate, and then you divide that by your sort of whether it's gender or ethnicity. The thing is, that relies on your ground truth labels, and are they fair? Are, in that world, black people and white people actually being caught at the same level of fairness? Definitely not. Predictive policing is a whole other issue that I'm not going to go into today, but policing and arrest rates are also discriminative. But in the hiring case, you kind of assume that your ground truth data set is ground truth and fair. And we can't assume that. We've seen loads of studies that show that hiring teams are discriminative. So equality of odds relies on the ground truth labels being pure and fair, and you can't necessarily use that as well. So we've now got like 9 different metrics. Which one do we go with? I'm going to introduce you to a wonderful tool and set of research papers called Aequitas. If you Google it, equitas.dssg.io, they have this, which is the fairness metric decision tree. Which metric do you choose based on what you're using it for? So is your intervention punitive or assistive? And several other questions. And it will guide you towards selecting maybe one or a few metrics that might be right for your use case. So next lab, we're going to just try out the Aequitas audit toolkit. So what I've done here is I'm just exporting data in a very specific format, the CSV format, so that I can load it up into this Aequitas tool. If you look at it, it is literally just the label value, the score, and the sex. And the Aequitas tool is an online tool. You can run it locally, although good luck if you're on macOS or Linux. The requirements are kind of a little bit ancient. If someone wants to make it work with NumPy 2, please do so. But otherwise, they do have a running version of this online you can access at their website. So you can audit your own data as long as it's in the right format. We can say, I want to have a baseline of on the sex attribute, and we're going to have men as our reference group. It's going to say which metrics you want to look at. Here's our fairness tree. So it's sort of really leading you through best practices here. And then you can generate a fairness report. And this has looked at my 400 rows of data that's come through my slightly hideous AI recruiter. And it says that kind of no matter which of the various metrics, I make this a bit bigger, whichever metric you're looking at, whether it's the equal parity metric, the false positive rate parity, FDR parity, false negative rate, that it fails in every single one of these. Now, obviously, because I've made it as awful as I could for this workshop, but this is a very good audit tool that you can use for yourself. And now it actually is going to explain what it is, why does it matter, which groups failed. Okay, it's saying women failed because 0.08x disparity, or I'll flip that, men are being selected 13 times more often than women, even though they have identical skills. So that's your equal parity. And there's lots of other sort of nice explanations. So really rate this tool. It goes into the details, into the weeds, and also if you have intersectionality in terms of young men versus old women and so on, then it can go into this intersectional comparisons too. Okay. Finally, what I'm going to do is now walk you through how can we combat all of this. We know how to measure it. We know if we have a problem. But what do we do about it? So I'm going to walk you through a little quick intro to a tool called Fairlearn. Before I do so, I'm just going to quickly introduce you to this worth knowing about. Again, if you're working in hiring, in the US, you have this thing called the 4/5 rule, which is the definition of legality for a decision-making system. So this is required by the Equal Employment Opportunity Commission. And if that number, that 13x number, or 0.0x number, basically if it's less than 0.8, 0.08 is a lot less than 0.8. If it's less than 0.8, then you can be sued as an employer if you are at less than 4/5 in terms of that parity of outcome. So if 60% of male applicants are invited for interview, no less than 48% of women should be invited for interview, as the example they've given here. In the UK, we don't have that rule, and there is a slight issue here, which is that all of these tools that I'm talking to you today, the open source tools, are built with a bit of a US equality and fairness angle, and the UK regulators have sort of come down on this and say, we're not sure about this. The 4/5 rule isn't a thing in the UK, and where are the AI open source fairness evaluation tools that work in the UK or in the EU? It's all a bit US focused. So they say, far from serving as a useful way to detect discrimination, application of the 4/5 rule in auditing tools may actually violate UK discrimination law, according to several UK experts. So just one thing to be aware of here, where is the line of legality is very much dependent on which jurisdiction you're in, which country you're in, basically, and what the rules are there. And in some of those countries, the rules may still be being made ongoing. I think the EU's AI Act is probably the biggest thing to come down the line, and we haven't got case law on that yet. So we'll see sort of roughly where it is. But in the US, it's a classic US regulation. You can go right up to the 4/5 rule and be okay. In the EU, in the UK, it's often more typically sort of principles-based. So if it looks like you're trying to game the system, then you're probably not adhering to the principles, as is typical in many EU and UK legislations. So finally, in the interactive part of this, let's look at Fairlearn. So there's quite a lot within this library. It's a library that's been sort of initially put out by some of the big tech companies, but it's been adopted as an open source standard, and there's a lot of stuff feeding into it. So I'm giving you a tiny, tiny glimmer of some of the things it can do, but there's a lot in there. All of those metrics and more are available within the Fairlearn library. So it's a Python package for assessing, mitigating bias. It has lots of metrics, and it's got lots of debiasing techniques built into it. I'm going to be walking you through just a couple of those today. So first of all, we need to get our head around what the Fairlearn metric frame is. It's a data frame with extra powers. You'll see some of those powers, but it can do sort of group bys very neatly across different subgroups that you might have when you tell it what those subgroups should be. So we've got our data frame coming in here, and we're going to specify as well. Some use the categorical pandas types. So we can see this data frame is 400 rows, 50-50 men versus women, and in terms of the selection rate, as we saw earlier, 41% on average people are selected. So we're now going to introduce this as, let's hide that away a bit, you can see more, the train test split, and we'll have a little bit of cross-validation going on. So now we've got 200 rows in our training data set. We've got 200 rows in our test data set. Sorry, 260 and 140. and I'm going to fit our bias, or refit our bias, LGBM classifier to this. So let's evaluate this, not just based on what we've done before, which is the accuracy of this model, but we're going to evaluate it on some of these other metrics that I've just been covering a moment ago. So this is the raw model, I call it. It's completely unmitigated. It's just kind of biased and terrible and a bit rubbish. You shouldn't use it on real people. So the fairness metrics, I've actually imported these. If you just scroll up, you'll see all of these have come out of the Fairlearn library. So you've got your equalized odds difference, false negative rate, false positive rate. It all just exists in Fairlearn. You can just import it. Kind of very neat, a little bit like scikit-learn, just has everything within the metrics module. So these are our metrics. I'm now going to create this metric frame for the unmitigated model. I've done nothing to it. It's just an LGBM model. And this is where the metric frame starts to showcase its sort of superpowers. So you've got the dot overall, just shows me those key metrics I was asked for. What's the balanced accuracy? It's sort of an imbalanced data set, so I've gone for balanced accuracy, 78%. What's the false positive rate? 1%, kind of want to get that lower, and the false negative rate, 43%. What about if we now split that out by group? And again, that just does it for you. So you can imagine this has got quite a lot of stuff going on under the hood within Fairlearn, where it's just calculating these breakouts all for you. So let's just read this and get our heads around it. You've got, for men, the model is 80% accurate. For women, it is 50% accurate. Again, it's biased training data. But that comes through in terms of how accurate it is. The false positive rate is 5% for men. Those are men that are being selected through to get a job or at least an interview who were not qualified according to high versus low quality. And for women, 0. So no women are getting accidentally favored. So bad luck. For the false negative rate, you've got 34% for men and 100% for women. So 100%, that's basically a lot of women who are being passed over in this data set. We can visualize some of this as well, so you can see, again, exactly how those look like. And when you look at this, this is what we mean by the sort of disparity. There is a disparity between false positive rate between men and women. There is a disparity between false negative rate, and there's also a disparity in terms of accuracy of outcomes. So we have a problem. We could measure any of these, but what is that difference? Let's actually capture that disparity as a number, and the number is the difference between sort of the top bar and the lower bar. So for balanced accuracy, there is a difference of 31%, 5%, 66%. So that's 66% between the false negative rate between men and women. In terms of the accuracy, we can also just bring that through. And there is one more thing we can do, which is an equalized odds. So how do we actually balance across these two different metrics, the false positive rate and the false negative rate? This is where I'm using the equalized odds to actually sort of combine them into a single metric. So this is my one metric I am going to care about for today. The equalized odds, for the people that do get selected, what's the difference between the false positive rate and the false negative rate between men versus women, captured in a single number, equalized odds. If equalized odds is high, you have a very unfair system. If equalized odds is low, then you have a very fair system. It's technically equalized odds difference between the two sensitive features. And again, in this case, the only sensitive feature that's going in is the gender column. We could add more columns. You could have multiple columns for intersectional analysis in this library. So I've got a number that tells me how good my model is on replicating previous decisions, which may not be a thing I really want to do, but it is at least a quality metric or an error metric. And I have a metric that defines how fair this model is. What can we do about it? So this is where the rest of Fairlearn comes in. First of all, the threshold optimizer. What this does is you've got decision thresholds within your models, like LGBM, many other machine learning, scikit-learn models. You've got your decision threshold. Do you give someone the job or not? Now, typically, the thresholds are set at 50% and optimized for that. What threshold optimizer does is after you've trained the model, it looks at the probability scores for each individual, and it tries adjusting the threshold, and it creates a different threshold for men versus women. It tries to get a little bit more fairness by adjusting the threshold, the decision threshold. So maybe it'll say, we can actually select more of the women by reducing that decision threshold and less of the men by increasing it. And maybe it's going to try and counteract it in post. So there's one thing to know about it. It happens after you've trained the model, and it uses the model outputs and those probability scores and decision thresholds to try and improve the stats, in short. So how do we use it? Super easy. Give it a model. Tell it which particular constraint we want to minimize. So equalized odds, it's trying to effectively try and minimize the delta in FPR and FNR simultaneously. It's going to get them both down with the equalized odds rather than just biasing one over the other. The objective is balanced accuracy. So I do want a good model. Don't just make it a completely random model. Like, try and make it good at selecting people, but bad, like, also make it good at being fair. And prefit is going to train a model, then look at the thresholds afterwards. So you can see it's looking at those probabilities. Once you've got this fitted, it's a bit like any other estimator in scikit-learn. We can fit it. I'm giving it my training data set here. I'm giving it the sensitive features. It does need to know the sensitive features. So again, if you were using this on your own company's CVs, do you have a data set which is just the CVs? Or do you have a data set which also includes their demographics? Probably not. It's not really that common for organizations to go through and tag demographics. Some organizations you have to. So again, we're working with the UK Government Cabinet Office, who are responsible for civil service recruitment. One of the things they have to do is to collect this sort of information, demographic information up front for people applying to jobs. I'm going to pause because there's a question.
Yeah, I was wondering, given GDPR kind of prevents you from gathering these features, does that make it harder to prevent bias in your model?
So potentially, yes. GDPR doesn't prevent you from gathering these features. Like I say, in many disciplines, you are either encouraged or you have to collect these features. You are not allowed to use those features when you're making decisions about people's lives, but the features are often collected in order to do post hoc discrimination or fairness research. So if we go back to that example, remember the St. George's Hospital back in 1979, one of the things that came out of that was universities must now collect people's protected characteristics at point of application. That doesn't get shared with the review committee, the decision committee. They don't get to see it, but it does get used by people who might want to do a fairness audit afterwards. So that's where it gets used. So it does often get collected. And the same is true with civil service recruitment as well. They see it as best practice. The same is true often when you go into a hospital and they might ask you to fill in a ethnicity survey or questionnaire. Sometimes it's optional, sometimes it's mandated. But these things are usually collected so that someone can take that data and, if they want, provide it to an academic who might be doing a study into whether there is racially motivated decision outcomes in hospitals or civil service job recruitment and so on. Question? So when we have the raw model is trained on the ground truth labels, the ground truth being what our horrendously biased recruiter function decided. Correct. So that is a key limitation. As it says here, a key limitation of this technique is you need the sensitive features to use it at prediction time, which is why this technique might be a good technique to look at. But if you don't have that data, then you can't use this technique. Yeah, really fantastic question.
I was just wondering, because this thing takes a model that's already trained and kind of shifts it around, wouldn't it be more natural to do it at the source, like when you train the original model? Or can you maybe comment on the difference?
Yeah, you all are very smart. You're leading into the next bit that we're going to do. So there's a whole different class of techniques. Brilliant question. There's a whole different class of techniques which tries to do exactly the same thing, but during training. And the short version is it's quite simple what it's doing. It's just shifting around thresholds, trying to improve outcomes whilst maintaining as much of the performance as possible. But there's lots of different ways that you can do fairness mitigation with algorithms. So this is one of them. And another is there's a whole class of techniques that tries to do it when you're actually training the model itself. And we'll see one of those next. Cool.
So when you shift the thresholds to a lower threshold, so what if the unworthy candidate gets a bit higher, even though it's the opposite gender, which they're trying to do? That's possible.
So you're saying, what if you sort of overcorrect in some ways? So you'll see when we evaluate this version of this model, we'll see what it's doing. We'll have a little look at whether it seems to have improved, whether it's overcorrected or not. But yeah. Maybe it could do. Do we trust these systems just because they say, hey, I fixed this? I don't trust anyone that claims to just fix it. I'm going to like hold its feet to the fire and check that it fixed it. Cool, we've got some time, so like questions are great. So just to repeat the question, you're saying if you only have one sensitive feature, and can you do more? Yeah. So absolutely, you can do this. It will. So these metrics, I'm sort of keeping it simple by just having just gender, but these metrics work at the intersectional level. So let's say. I wish I could bring up some of the slides of the work we've done for DSIT. It's still under embargo by the UK government. But what we did there is we looked at a group that could be late-stage career men, white men even, all the way through to mid-stage, younger stage. Then you have women, and then you have other ethnicities as well. And the standard ones used in the UK are white, white other, black, and Asian. Typically the 4 groups that are used in standardized research. So that's what we did. So then suddenly you've got like 12 different groups that are coming through. If you were to, or more. I think 24 different groups, 4 by 2 by 3. And this will look for the maximum disparate impact. So if you have your, let's say, young white men being selected for a software engineering role 20 times more often than an old black woman, then that will be a huge disparate impact between those 2 groups at the intersectional level. And if the only thing that's changed between them, if that's actually 24 people who have identical CVs and the only thing you're changing is a little bit of clues in their name, then you've got a very, very illegal hiring system. But that is kind of the stuff that we saw LLMs doing. So if they're being used for recruitment, then there's a huge questions about whether that's legal or not. So we'll come on to this in a little bit, but there is a trade-off between how fair you want to make your model and how accurate in replicating historical decision-making you want to get it. So accuracy or performance or error versus fairness. And as you add more intersectional groups, then you are potentially adding more constraints. You might be making it fairer, but also you are degrading your model performance. I've got some thoughts about sort of how bad is that to come. Cool. Like I said, we've got some time, so if you've got questions, just throw up your hand. But otherwise, let's see how this threshold optimizer actually does. So we've got the thing, it shuffles around the thresholds, it tries to figure out if we reduce the threshold for women and increase it for men, maybe we can make it fairer without too much loss of accuracy. So is that true? So we fit it. It's a post-processing technique. It does need access to your protected characteristics. And then once you've done that, the code, what you'll see again, like if you're looking at this code for the first time, there's a lot of new code. But just like using scikit-learn, once you've written it once, it's kind of copy-paste over and over again. It's the same methods that we're using every time. So we've got our metric frame. We can then just do what's the overall. So 78% on balance accuracy. False positive rate, I think, has actually gone up a bit. False negative rate has come down a lot. We'll do a comparison shortly, but we can visualize that by group. How is this looking? So certainly the false negative rate for women was at 100%. Now it's only at a whopping 75%. And men have gone up a bit. So now more men are being passed over correctly, according to this data. And the false positive rates has also come down a bit for men. So we can visualize that. And if you're a visual person, if you remember what we had before, I'll just scroll out for comparison. There was a big disparate impact previously. And now that difference between the men versus women bars is going to be less. We haven't like eliminated it. It was a horrendously biased data set, so we haven't eliminated it, but it has improved it, which is still better than not improving it. So if we were to capture that in a single number, what is now the differences? We can feed those in, calculate our balanced accuracy score and an equalized odds score. And we'll look at how they compare with the unprocessed model shortly. But let's use one more example. There was an entire category of techniques in Fairlearn called reductions. And this is exactly what the gentleman here was sort of alluding to. What if you could, when you're training your model, get the model to sort of take this stuff into account? And don't just optimize for this one thing, but try and optimize for this other thing too. So these are reductions. Now, I'm not going to go into the weeds of the mathematical details of how this works. This particular reductions approach is called exponential gradient. Have a little look on the Fairlearn website. There are many others that you could use as well. So a bit like when you're doing model selection, model tuning, this is similar. You can do mitigation model selection and then tuning as well on top to try and get the numbers to where you want to get them. But what is this doing? It uses reweighting in the model training process. So it creates a sequence of reweighted data sets. It trains your base classifier. This is still the LGBM classifier that we're using. It trains them on each of those data sets and sequentially tries to reweight them to satisfy your performance or your error, like keeping your error low, but improving your fairness as well. So it's using a lot of, it's a bit like bootstrap resampling, but sequentially, and it's just sort of tweaking things iteratively. So quite neat. It's enforced the fairness during the training, not after. It doesn't need the sensitive features during prediction time either. So once you've trained this model, you don't need to know a new CV comes through. You don't need to wait until someone makes some assessment of whether it's a man or a woman for it to work like it does with the previous example, which would just be kind of weird and maybe illegal. So it's got benefits on that front. You've also got some parameters. So like model tuning, you can tune these parameters. You can figure out which one gives you the best results. So let's try it out. So a little bit more complicated to set up. We give it an objective. I want to try and get my error rate. Currently it was high-ish, like, I don't know, 0.14 FPR for men, and it was really high, like 0.7 for women on FNR. So I want to try and get my error rate down to 10% on both fronts. Then I'm giving the constraint, same constraint as before, equalized odds. I really want that fairness to improve, so equalized odds as low as possible, or equalized odds difference as low as possible. And then we've got our reduction tool is an exponentiated gradient. Feed in the model, feed in the constraint, feed in our objective, fit it to our data. This stuff is kind of a little bit rinse and repeat compared to the other tools. So really consistent API design here. Very nice job by the Fairlearn team. We can now make some predictions. We can see how this new sort of fairer during training model is going to work. So we're going to feed it into a metric frame so we can actually do our analysis. Think of the metric frame as you've got the model, you've got the outputs, you've got the predictions. Let's see how good it is. So this code is identical to what you've seen before. And at this point, I'm a very visual person, so I'm going to look at the visual version, and we can see that our balanced accuracy is a little bit worse, actually, if you compare them. The false positive rate may be better. False negative rate is actually where we've got the biggest gains. So even though the false positive rate is really high, you still got a lot of men who are being selected into jobs and maybe they shouldn't have been, but you've got a much lower false negative rate, a much more balanced false negative rate. And to be honest, like, it is okay to have false positives and it's okay to have false negatives. But in this world, we just want to try and make sure the false positives and the false negatives are not massively biased towards one protected characteristic or the other. So you've still got men and women both being overlooked on the right-hand side here, but it's more equal in terms of this protected characteristic. Question?
Sorry, I'm going to try and shout. What's the law say about using protected characteristics as
I think UK law doesn't have much to say at the moment. I am not a lawyer. I have spoken to the HRC about these sort of things, and they're trying to figure this stuff out. I guess like one way of looking at it is how do you enforce it? How do you know what people are using in their training data? You shouldn't be making decisions that discriminate on protected characteristics, but there's a lot that's not being said there, and how people use algorithms is kind of different. Now, if you're in China, it's kind of an interesting world because they actually do force a lot of their AI companies to give the government the training data and the models that they're using within any apps that are deployed at citizen scale. And again, I don't do too much about this other than like that is how things work in that country. So like that's an interesting system that would mean that you could then enforce what you're talking about. And then you could say you shouldn't be using this. But how it's working in the UK, open question as to how this is going to work. I think the first thing we need to do is actually test some of these systems and move forward to the whole world of AI assurance, which is a very, very native discipline at the moment, I would say. I'll have more to say about that and like what the latest stuff that the government is doing on AI assurance and bias and discrimination and fairness at a more high level in a bit. Question?
Yeah, how come you can't get the false positive rate for all metrics to be more or less at an equal level? Like, especially with the threshold optimizer, that shows this approach. Feels like it's just a question of tuning up the threshold to the right point, so it actually is equal. But somehow that doesn't seem to be possible, and there's still a disparity even after you apply those approaches.
Yeah, I think this is kind of whack-a-mole with metrics. You can get the orange and the green, you can get them exactly, well, not exactly, but you can get them very, very even if you have a coin flip system. Okay, you get the job completely at a coin flip. Okay, false positive rate, false negative rate are going to be completely even, but you've also got a useless model now because it doesn't help at all. Like, hey, do you want a job? I flip a coin, and if it's heads, you get the job. Like, that's not a useful model, and your accuracy then drops to 50%.
So these approaches do have some tuning parameters that say, let's keep the model working to at least this degree type of thing, and that kind of constrains them.
Yeah, so this is constrained optimization. The constraint is I want to try and stay within a 0.01 difference in equalized odds. It's like that sort of balance of FPR and FNR. So we want, like, keeping within that, give me the best accuracy you can. And we're defining that with the objective of balanced accuracy. So constrained optimization. But yeah, as you try and, I don't know, if you try and optimize false positive rate, false negative rate goes through the roof. And if you do it the other way, false positive rate goes through the roof, which is why we're looking at equalized odds, which is a little bit like the fairness equivalent of F1 score. Like, don't just optimize for precision over recall or vice versa. I need both of them to kind of be good. So that's why we're looking at equalized odds typically.
So let's imagine I have a binary classification class, right? And I'm not really interested in fairness. So let's imagine. And I know that in my data set there are slices with underrepresented number of samples. So the number of samples is quite low. Do you think it would be possible to use these techniques to improve the generalized ability of the model, for example, or improve the performance somehow on the underrepresented parts?
So I'll just repeat the question. Is it possible to use these techniques in a sort of adjacent objective goal where what you're not trying to solve for is fairness, but just a completely different sort of problem where you just have a very imbalanced data set and some subgroups are very underrepresented? So this could be, I don't know, like equity trading, where you've got most of your equities are oil, I don't know, like oil futures or something, equities, futures. Maybe it's in one industry, and you've got a very small sample in a different industry. I think, I don't know is the answer to this. I haven't tried these techniques for non-fairness applications. What I do think is that the concepts of fairness, I think, have business objectives or applications beyond fairness. I think if you care about models that are not biasing towards your majority groups in your data, okay, so let's say we're building a recommendation system, and you've got your UK customer base, and now you've just launched in the US, and they've got a tiny US customer base, and their behavioral preferences are different. You know, maybe you're building like your Spotify style music recommender, and people listen to different kind of stuff. Do you want your algorithm to be biasing towards the preferences of the majority group, or do you actually want the US algorithm to be working a little bit better? You could actually just build two different algorithms, I don't know, but it's something that's worth thinking about. I think the actual business applications of these sort of tools go way beyond just discrimination and fairness into building better AI systems that work better for the smaller subgroups within your overall data without just building loads of hierarchical models. Cool. So we'll sort of wrap up this section. Let's see schools and the doors. So we've got 3 different techniques. One is completely unmitigated. One uses the post-processing, adjusting decision thresholds, to try and add a little bit more fairness into the mix. And one actually uses a sequential reweighting process, trying to find the best way to reweight the underlying data to train a model that actually is accurate, but also still fair. And I'm sort of rushing through this bit because you're going to see the numbers visualized between all of these. So we've got unmitigated, we've got the post-process, and the reduction technique. Let's see some numbers. I like numbers, but I like graphs even more. Ooh, that's turned into a line graph overnight. Interesting. So, crikey, you're going to have to interpret that now. The joys of, I'm just going to rerun this just in case it's a random unlucky error. No, it's really consistent. OK, what you've got is you've got a trade-off here. And I'm just going to interpret these numbers quickly. So you've got unmitigated, 77.8% balanced accuracy. When we do the post-processing, we actually improve the accuracy remarkably to 78%. And then as we go to the reduction, the accuracy is now dropped to 73%. So there is potentially a trade-off. But what about the fairness, which we want to get as low as possible? The equalized odds was at 66, 0.66. Now we want this to be as low as possible. The post-processing at 0.47 and reduction at 0.48. So if I was just putting these together, I would say actually the post-processing seems to be the best combination here. It gives me the highest accuracy of all 3, and it gives me the best fairness of all 3. And I'm just going to try and interpret this, see if this is saying the same thing. So you've got 3 different models effectively represented here. They should probably be blobs, not lines. But you've got one model which is much better than the rest. It has the best accuracy, and it's low down. It's the most fair. So I'd say that's the best model. When I ran this last night, it was actually way more in the middle, so it's interesting that it sort of shifted around. But this is quite typical to see that you have a trade-off between these things as you move around. And what do you want? Do you want better accuracy, but less fair? Very typically up here to down here is where I'm used to seeing things. You have stuff that's highly accurate, but less fair. And you have stuff down here that's much less accurate, but more fair. And somehow our post-processing has just come along and ruined my workshop by being the best at both. And maybe that's a good thing. So we've got these trade-offs. I'm going to just bring back some of what we typically see when people have researched this at scale. So the fairness accuracy trade-off. There's a wonderful book. If you really enjoyed this and you want to learn more, one of the resources I can recommend is The Ethical Algorithm by Michael Kearns and Aaron Roth. There is a good podcast interview with Michael Kearns out there on YouTube, so you could have sort of the short version before diving into the longer book, but the book has nice pictures like this. So there is a Pareto front typically between error and unfairness. As model error increases, then unfairness, you can optimize for fairness rather. And if you want to minimize a model error, then what you're typically doing is maximizing unfairness. So there is a Pareto front between these two things. And as a result, that's a challenge. And this has been backed up. There's lots of examples that Kearns includes in his book around this using real-world data of what that Pareto frontier looks like. So just to make sure you sort of grokked this graph, this model, if you end up using this model, it's really bad at fitting the training data. It's like the example we talked about over here. It's almost a random number generator model. Like it's useful for maybe nobody, but it's incredibly fair because it's just making decisions completely at random. You know, it's like a roulette wheel. So is that a good way of making decisions? Well, it's not going to get you your next VC round because you've got a useless model. So what is going to get you the next VC round? Let's minimize our error, but that's also the most unfair model you can choose. If you're just focusing on pure performance, minimizing your model error, whether it's your recommender system, whether it's your loan application system, whether it's your equity forecasting system, if you just focus on this, then you might also just be maximizing unfairness. In reality, and this is the biggest opportunity I see, most of the models we ever have in the world are actually not on the Pareto frontier. If you are on the frontier, then like good for you, but most of the time we're not, which means the opportunity is if you do a fairness audit, you can probably maintain your accuracy of your model. If your team seem kind of cool with it, then great, lock it in, but get the fairness down. Like really improve it for fairness. One slight concern is like, why would any organization do that if they realize that you're not on the Pareto frontier? They might actually just say, yeah, I don't know about fairness. Like, just maximize that error. So bring in some more machine learning engineers and do your thing and make our models better. We don't care about fairness. And that's a problem. Like, we do live in a world where organizations may not be incentivized to care about discriminatory outcomes of the systems that they build. So what do we do about this? Just a little bit of insight into also some of what we have done about this. So I can't tell you yet exactly what we did for DSIT, but I can give you some ideas of what we probably did for DSIT because it was inspired by this Bloomberg article. What they did is they threw a ton of CVs, very much like what I've done with you today, at GPT, just GPT 3.5 and 4, so this was only March 2024. And they showed very conclusively that it is a great tool for recruiters. Like you absolve your decision making. Cognitive offloading, I don't know if everyone's come across that term yet, but it's probably a term for the future. Just delegate decision-making responsibility to the LLM. Recruiters do like it because it saves them time, but also it's racially biased, is what Bloomberg's data team proved. So very similar to what I've been walking you through today. They had identical CVs, different names, very similar to that DWP study. They threw these names sequentially into OpenAI over and over and over again. They generated resumes from it, and they had job descriptions, 4 different jobs that they looked at, so they could see there were differences between jobs. It turns out OpenAI, the GPT model, selected different people for different jobs. For a software engineer, it would go for sort of like a young white guy. For the US retail manager, it would actually be a more experienced Asian woman came out top out of all the different demographic profiles that they had. So they basically got GPT to rank from 8 CVs representing 4 different ethnicities multiplied by 2 different genders, got it to rank, and then they just did that again and again and again until they had some statistically valid data that showed maybe this thing is somewhat biased. So these techniques that I'm talking to you today, they are very good for the sort of the models that you can easily tune, like a scikit-learn model that has a .fit, .predict style endpoint. But what about if you're using Gen AI? Then this is the sort of design that you might want to go down to measure it. And as for mitigating it, we're in really, really gnarly territory there. So if you want to know more about that, come and speak to me afterwards or come and find me in the pub at any point this weekend. You can measure it. Statistically, you can see if these things are statistically discriminative. You can look at the fact that it is ranking certain sort of ethnicity, gender combinations well above others. And therefore, you've got the equal treatment metric graph on the right-hand side here that says that, in this case, you probably can't see it, but it says Asian women at the top with better treatment on 17% of runs. Right at the bottom is black men, and this is for, I think, a finance manager role. So Asian women, Asian men, then you've got everyone else in the middle, and right at the bottom, black women and black men. This is how GPT-4 makes decisions if you throw 8 identical CVs with different names into it. So this is all public, this is all Bloomberg's work, not ours, but it inspired our work because we looked at this and we thought, well, GPT-3 and GPT-4 are kind of old. There's some new ones now, and there's also Claude, and there's also Llama, and there's also a whole bunch of other ones. And also this is US names and US job titles. Well, what if we do this at a much greater scale and do it in the UK? So that's effectively what we got commissioned to do by DSIT. And they have all these different examples of, for the HR specialists, Hispanic women do really well. White men do not well at all. Financial analysts, again, Asian women and men right at the top. So these things are different. Think back to that Hollywood casting. That's the person who gets the gig. And they also did some really fun things looking at the embeddings and realized that, of course, models perceive names in sort of racially ethnic groups. Of course they do. Right? You know, that's what they've been trained to do. So some closing thoughts. Why should anybody care? Like I said, if you are in a VC funding company, you've got a CEO or CTO who says, I need the best performing model. I don't care about fairness unless someone's going to make me do it. And the EU's AI Act is coming along, 35 million euro, or I think it's 6% of your global revenue, something like that. It's pretty punitive if you get caught out. But there also have been some case studies already in the US. iTutor Group, they were a education and hiring tool. They use AI software to automatically reject older applicants. I don't think they set out to do this, and I don't know anything about the internal details, but I have some guesses, some hypotheses. They are a Chinese company that launched in the US. In China, at the age of 60, if you're a woman, 65 if you're a man, you have to, 55 for women and 60 for men, you have to retire. Almost everybody will retire at that age. So in their training data, they might have a little bit of a hiring cutoff cliff based on your age. And what happened in the US is when they rolled out this software there was a particular woman that became a class action lawsuit. She realized if she adjusted her age from sort of 62 years to 59 years, suddenly she was getting the callback for the job. So it seemed like a really hard-cut cliff in terms of selection criteria, which meant that it was kind of easy to prove in a class action lawsuit. It was the ideal example of a very strong bias encoded into an AI algorithm that was being used for selecting and deciding whether people get jobs or not. So it revealed age bias. After many years of legal wrangling, they settled for $365,000, which may be a lot or maybe not a lot, depending on the company. But that's sort of the level of punitive fine for doing this stuff or not caring about this stuff. My sort of hypothesis is really easy to just do a little bit of this. So thank you all for coming along to this workshop today, because you can start implementing some of these ideas into your own workplaces. You shouldn't have to wait for someone to get scared of a fine to do the right thing. It also might give you a better system. One more thing to think about. I don't know if anybody's read this book, Weapons of Math Destruction by Cathy O'Neill. But this example is from that book, and I think it's a really, really insidious example of how building AI systems can cause pretty harmful feedback loops that just get worse and worse and worse. So here's how it started. 2015, the Washington Post said Google's algorithm is showing prestigious job ads to men, not to women. If you search CEO in Google in 2015, you get basically what looks like my ChatGPT picture. So this was a problem. If you search CEO now, Google is obviously aware of this. I think it kept on coming up in the news. They have done a lot of work to fix this. This is 2024. But here's the concept. The concept is still absolutely valid, and watch out for it in your workplaces. So what's happening is you've got a situation where training data is being updated by the algorithm's outcomes, its decisions, and then that's feeding back into future training data. So here's how it works. If Google thinks you're female, you will see fewer ads for high-paying jobs. This used to be true. Again, there's a reference in the chat, in the slide. Therefore, you are going to get fewer high-paying job offers for high-paying jobs. Again, this is the aggregate of just men versus women. You will get less job experience on average. You become less employable than your male peers. The algorithms see, oh, women are less employable than men. Like, let's show them the lower paying jobs more often. And so you get the feedback loop where the historical data suggests that the algorithm was right all along, but it's sort of feeding into its own decision making. So this is a thing that can happen. And it doesn't have to be a fairness issue. This is just a straight up algorithms doing the right thing issue, which if you're purely focused on profit, this is still worth considering. Any situation where your algorithm is making predictions that changes things that then feeds into future training data, you might have a negative feedback loop. So watch out for that. So how bad is the harm? At least in the world of hiring. AI-enhanced hiring tools are not too commonplace, so I think that is very, very rapidly changing. At least my applicant tracking system suddenly just popped up with a new section full of CVs from I don't even know where. So there's some AI happening, the AI recruiter. So I think that's changing pretty rapidly. And companies are going to start using it if it's going to save them time. It's very, very much systemic. It's hard to measure. It's not individual. What's individual can go and raise an employment tribunal saying, I didn't get this job and I think it's because you had an AI. So, it's really hard to do this. This is a really hard and insidious problem to solve. It's hard to measure, it's hard to prove. We can measure it as practitioners of the people building the models. That is the one very good thing I can say. So share this once it goes on YouTube with anyone who think you can benefit from it. As developers and companies, we can do this for ourselves, but governments will start doing this as well. There is a new tool currently out in consultation from the UK government called the AI Management Essentials. At the moment, it's a very, very dull checklist. If anyone has ever gone through Cyber Essentials, it looks like that. But it is a good standard. If you are procuring AI vendor tools and you want to hold them up to account, just send them the AI Management Essentials or AMI checklist from the UK government and say, can you answer these questions for us? We want to know if you've done your due diligence on how you've built the models that we're now going to use, and potentially, as companies, you could be subject to an employment tribunal if you haven't done your due diligence on those. Does anybody care? So again, ChatGPT selected Asian women 2.5 times more often than black men for an HR role. This is not a great situation to be in terms of LLMs doing decision making, whether it's for fraud, whether it's for hiring, whether it's for any other loan applications, the rest. We're shifting into a world where the historical discrimination is just fully baked into LLMs, and the benefits are super obvious to a lot of people, but I think those downsides are very insidious. 47% of Americans think that AI does a better job at humans than treating job applicants the same. So humans, we know that humans are bad, and that LLMs are going to be kind of bad as well, unless we figure out how to make the LLMs better and those AI systems better, because we can do that because we've got the fairness mitigation tooling at our disposal. What we shouldn't be in is a world where 90% of people feel like they have to change their names just to get a job. I think that's kind of sad. So if you want to learn more, we did do a lot of knowledge sort of communication, some little blog posts as part of this project. So you can check that out at fairnesstales.com. I'll put a link in the chat. Or you can scan this. We've got some fun case studies of AI going horrifyingly and entertainingly wrong. And otherwise, thank you very much for coming along. Thank you for staying with me. If you want us to come and do an AI audit for you, come and talk to me. I've got 3 of the Cathy O'Neill books to give away. So again, first few people come and get one. They're yours. Otherwise, thank you very much.